Sorry I'm a little late. So we had the quiz. Let's see, I need to go through the quiz first. Some been computer problems here, but that's okay. So we had this the quiz is on this paper by Lee, looking at the structure of graphene oxides. So this is it's a material. So it was first discovered with the let's see, there's the quiz here. Get that out. It's this Beam and Geem and Constantine, who are at Manchester University in the UK, and they took a piece of graphite, which is just a mineral that you mine, right? And it's got flat surfaces on it. And they just took a piece of Scotch tape, put it onto the graphite, and peeled it off. And then on that tape were like sheets of carbon, right? So like aromatic kind of aromatic cage structures. I mean, something like that goes on. So it's going to be a 2D single atom layer thickness. So again, like double bonds are in a plane. So if you have this molecule, that's all these units are in a plane, just like I drew it. So this thing's going to be a completely planar molecule, right? It's all conjugated. Things like single, double, single. Somehow I didn't draw this right, but it should go everywhere that you go is single, double, single. Right, so that means the entire structure has to be in a plane. Right, so you can do that with carbon. I can't draw it here, but basically it'll be just single, double, single, so conjugated in every direction. Right, so let's see, some of these carbons have too many bonds. That's a problem. This guy's got 1, 2, 3, 4. That's okay. Anyway, some of those are wrong. Anyway, so anyway, they were able to just pull this off, and then they got single sheets of they named it graphene after some like if you have ethyl, then you call it ethylene. It's got a double bond in it, right? So ethane would be like a single bond, and ethylene would be 2. Came from graphite, so they just called it ene because it had double bonds in it. And it's just kind of like a name they came up with. Then they proposed that you could do this is conductive, right? Because it's conjugated. If you dope it, it'll conduct electricity. And then it's going to have some special features because it's like rigid. So it's a rigid planar 1D structure. Then it turned out, so people got interested in this, and then in 2010, so they did this around 2000, and then in 2010, they won the Nobel Prize for this. It's pretty simple, Scotch tape and graphite. I mean, you can get graphite they use it for lubricant. You know, graphite's used to lubricate because these sheets slide against each other. So it's a pretty common mineral, and it's not expensive, and they can make this nanomaterial from it. Right, the Scotch tape wasn't a really good way to do it. In terms of making large quantities, so other methods were come up with. Once they figured out that you could get these graphene sheets alone, then people looked at kind of this process of taking a sheet structure and then breaking it into these individual sheets was known from clay. So you can do that with clay layers, and in clay it's called exfoliation. So foliate means leaves. And then X means to kind of remove, I guess. So remove the leaves. So you pull off the sheets of it. So this using Scotch tape as a method of exfoliating graphene. Usually with clay, the way they do it is you come in with, you'll modify the, so clays have an ionic interaction that binds the layers together. So you'd come in with chemicals, particularly polymers can weasel their way into this gallery, they call it, between the layers. And then that, if it's a charged polyelectrolyte, it can separate these and then you can exfoliate a clay that way. Ended up with single layers of clay. With graphene, they kind of use the same thing, except this isn't a charged structure. So clay is a charged structure, graphene isn't. So you have to introduce charge. To introduce charge by putting in a strong acid, and you can introduce oxygen into here, and you get graphene oxide, like oxidized graphene. And that is going to be the similar sheet structure, except some of these double bonds are going to have like OH sticking off. So you break the double bond and you put an OH, which means it's not going to be exactly as planar as the graphene was originally. So it should have some kind of kinks in it. Also, it means you're going to introduce this ability to solvate it easier. For instance, you can put graphene oxide into water, but graphene wouldn't go into water because it's hydrophobic due to the hydrophobic effect, right? So basically, with this material, so they did simulations. These are results of, I think it's Monte Carlo simulations they did on the sheets, and they get this structure. Right? This shows you that the thing isn't planar exactly. It should be perfectly planar, but it's actually got some kind of structure to it, some kind of convolution. And so they show a planar sheet at the bottom, and they define, so if you have a polymer chain, then you define the contour length as like going along this pathway. Or if you could fully straighten out, that would be the contour length L. So you have the size R and then the straightened out size L, which is proportional to N. L is the same as N for a polymer, for linear polymer. So in an analogy to that, they take the sheet, which you can draw in cross section, and then if you straighten out the sheet, you'll get a contour length L, but in this case, it's going to be proportional to like N to the 1/2, right? Because this is actually a 2D sheet. So it's L squared would give you N. Right? So there's a difference between, this is graphene or a 2D manifold. So 2D manifold means that you have these sheets. If you look at, so it's a 2D structure if you straighten it out. And then if you look at any local point, it's got a 2D structure. Like you zoom in enough, it'll be 2D in that small area. Just like for this, if you take this chain and then you zoom in, you'll see a rod. So it's 1D in a local area, which means you can map it. So you could map this chain with a series of 1D maps. Like it could say the chemical composition, and then that would be a 1D map for this chain, but the chain's actually convoluted, right? So any 1D map couldn't represent the whole chain. The same way here, you can do 2D maps locally, but the entire structure can't be mapped with a 2D map because it's convoluted. So the dimension's higher than 2. Right, and the classic example of that is the globe. So you say like the globe, so you make a map of Ohio, what it looks like, and then basically it's a 2D map, but basically Ohio is actually curved because it's on the surface of a sphere. So you can do a map of Ohio and Ontario and Antarctica, or Arctic and Arctic and Central America. You can do a bunch of 2D maps, but they won't all add up to the globe because none of those have a sphere in it. Right, so you don't get the, so it's a 2D manifold, but it doesn't mean that the thing is 2D. Like a sphere isn't 2D, but locally it is 2D, so it's a 2D manifold. Right, so some kind of wording that people came up with to talk about these things. Then, so there's a problem with these systems that first they're black. Okay, they're pitch black. So any amount in any solvent is going to be black. So it's going to be similar to the paper last week. There's an absorption problem. Like if you want to shoot a beam of light through this, you're shooting through black, which means no light comes out. Right. So most of the optical techniques aren't going to really work with this. And then it's difficult to to do TEM on this. You'll get something like this picture here. So you have to dry it out to do TEM. And it's going to come out looking like these things, or this is SEM. So these are pretty large sheets. So then you're kind of left with, there's not many ways to characterize this thing. That's kind of the issue. So this group, so this is pretty new. It's like last summer, I guess. They figured out that you could do intrinsic viscosity with this, right? So what are you going to do with intrinsic viscosity? Well, you have that this is going to be, so you have the solution viscosity and the solvent viscosity, and then you're going to do a Taylor series expansion and concentration, and then you have this number, this intrinsic viscosity number, which it's not viscosity, it's going to be like 1 over some concentration, and that concentration is the overlap concentration, with the concentration that the object carries with it. Right? In other words, within a polymer chain, if it's a fractal object, it has concentration with it. So that concentration is C star. Right? So that's going to be the mass of the chain divided by the size of the chain. And if it's a fractal object, the size goes with the mass to the 1 by df. So this thing ends up being n to the 1 for that one, minus 3 by df equals this C star. And this intrinsic viscosity should be 1 over C star. So the intrinsic viscosity should go with n to the 3 by df minus 1. And then df is 2 for a sheet, right? So you expect it to go to n to the this is 1.5 minus 1 to the 0.5. So for a Gaussian chain, so df is 2, 0.5 for a sheet, df is 2. It's just got to do with the density of the object. And it turns out that a sheet, if you spin it around, has the same density as a Gaussian chain. Right? So you're thinking about a sheet, but you're spinning it around, so it has a volume that it fills up, and then the same with the polymer chain, you're spinning it around so that it fills up a certain volume. That volume's R cubed. And here it's going to be kind of L cubed, more or less. Right? So anyway, so basically you're going to get this intrinsic, this A parameter. So you say that the intrinsic viscosity goes with n to the A, the Mark-Planck equation. And then the A is giving you what kind of the density scaling of the thing. And if it's a Gaussian chain, you get 0.5. If it's a 2D sheet, you get 0.5. And then if you have a convoluted sheet where df gets larger, right, then this number gets smaller, so you get something less than 0.5. So if it's convoluted, it's going to be like 2.5, and then you're going to get convoluted 2.5, you get 0.2. So he says in the paper that convoluted good solvent is 2.5, and he gets that from this equation here, gamma. He doesn't give a basis for the equation, but he says gamma is 2 plus df over 5. Because we're always in 3D space. So the bottom part is 2 plus the spatial dimension. So if df, not df, d min. So the object's, not d min, c, sorry. That's the object dimension, base dimension, or topological dimension. So that for a sheet, c is 2, for a linear chain, c is 1. Right, so 2 plus 1 is 3, you get 3/5 for gamma, which is, gamma is 1 over df. So df is 5/3 for a, okay, so this equation works, you know, for the Flory-Huggins, except that Flory-Krigbaum, but basically we know that Flory-Krigbaum's an approximation. So this is an approximate equation. In other words, it should be, the df should be 1.70, and this thing gives 1.67. Flory-Krigbaum approximation, Flory-Krigbaum exact. Like if you do a numerical integration, you get 1.7. If you do an approximation, you get, if you do an approximation, you get 1.67. If you do a numerical integration, you get 1.7. So this equation doesn't work for the reality, but it works for the approximation. So who knows how, it looks like this was just more or less extended from that because it worked for this number. And then now they're going to say that works for 2D also. Right, so this isn't exactly a good equation, right? So you have, in that case, C is 2, so you get 4/5 here. And then df is, then gamma is 4/5, and df is 5/4. Let's see, df, is that right? 2/5, 1.67. 2 plus c, d star is 2, right? Self-avoiding tethered membrane, 4/5, yeah. So that's his gamma. The gamma isn't exactly df. This part isn't right. So it's df for, it's 1 over df for the linear, but it isn't for the sheet. So this gamma is just Rg, or his some coil size equals L to the gamma. And it's not equal, it's proportional to, right? So he says proportional here. So it's just proportional. So the size of the thing is proportional to L to the gamma, meaning the size, meaning when it's crumpled up, it's got some size R, and then it's got this size L, which is if it was extended. And those two are related with this power, and that's the power. Right, so it's a little bit involved with powers, and the bottom line is he wants to know, like, what is the structure of the sheet? Like he can simulate it and get the structure. How are you going to measure it experimentally? Like, how do you get a size for the sheet experimentally? You can stick it in a microscope, get this, but the thing's squished down onto a carbon grid or something. Right, so you can't say that that's actually the size. So he wants to know what's the size in solution. So he puts it into DMF, which is this solvent that's used for DMF's this thing. So it's used, so it's amide, so amic acid, or dimethylforamide. So formaldehyde is like double bond with 2 H's, right? And then you put an amide. So you put amine here, and it's a dimethyl amine. So you got 2 methyl groups. So it's dimethyl amide, formaldehyde amide, right? Formaldehyde's that thing sticking on. Amide's this thing. Amide with 2 H's. Then it would be this dimethyl because it swapped the 2 H's with methyls. So it's a common solvent. Apparently it's not toxic, not particularly toxic. And it's good for, it'll solubilize most carbon nanotubes, buckyballs, and graphene. Right, so you'll see everyone uses DMF. It's a good solvent for this. And it works for graphene oxide. You can also use water. So usually you'll do the separation, the exfoliation in water with sulfuric acid and a lot of heat and whatever you can throw at it. And then you'll get something out of it. And then precipitate in methanol and then put it into DMF. DMF's the preferred solvent, but you can't put it, you can't put it concentrated sulfuric into it. So you can't do your exfoliation in DMF, but you want to have it in it afterwards. Anyway, so there's a lot in here, but it's a simple experiment, right? So basically, I wanted you to get the idea, like you could build this yourself, right? So basically, you need a glass tube, and then you need a glass blower, and then you can just build this thing. Right? It's not going to be hard to make this. You could make this yourself. That was the idea. So you start with this glass tube, then you get your glass blower to just heat it up and blow air into it, and you can make 2 bulbs. Doesn't matter the size of the bulbs. Right? You're just going to measure the time. So the size of these things make no difference, except that you want to have enough space here so you can do your dilution on this side. So you can see this is a bigger tube on this side. So this tube's been drawn out on that side. Then you heat this up. In the old days, everyone would do their own glasswork. Like you would just do this, you know. So it's good to kind of think like you're going to make this. And then you're going to heat this side up and pull it out. You narrow down this tube until it's a fine capillary, hopefully a uniform diameter, and long enough that the end effects don't matter. You can't see the capillary here, but it's just a thin line in the middle. And then this is the tube you started with over here. You bend it to get a U shape. Then you make a bigger bulb over here, and maybe a wider tube. You can make a giant bulb over here. This side doesn't matter, except that you want to use it as a container to do dilutions. Then you put your solvent in. So you wash it out so there's nothing left in it. Then you put your solvent in. You measure the time it takes to flow from a red mark you make here to a red mark you make here. Nothing's been measured. You don't have to measure anything, right? It's just going to flow through this tube. It'll follow Pascal's law, and it's just the time from A to B. You don't need to know any of these volumes. Just measure the time. Then you have the time for the solvent, time 0, and then you put in your solution. You put in the most concentrated solution, but you put it in so it just barely fills up the tube from the bottom of this to fill up this bulb, because you're going to dilute this thing. So you want to have empty space. Then you do your time again with that concentrated one, and then you put in some solvent and mix it up by pushing it back and forth until you feel like it's mixed. And then you do it again with the next diluted one. So usually you dilute 50%. Then you dilute it again and again and again. And then you get a series of times with concentration. So say concentration is 5 mg per ml, then you get 2.5 and you cut it in half. And you get 1.75, and maybe you get 0. Whatever that ends up with. 8 something, 875 or something, right? And you can cut it again. So you do like 1, 2, 3, 4, 5 cuts on that, where you keep adding in equal volume of solvent to dilute it down. So you have to measure the amount of material you put in at the beginning, so you can do the dilutions to get the concentrations. You need good numbers for the concentration, but otherwise the time is relative. It's all relative. So you're just going to say that the viscosity minus the solvent over the solvent is going to be the time of your run minus the solvent time over the solvent time. That's Pascal's law. Then that divided by the concentration gives you the specific viscosity, gives you the reduced viscosity, and then you plot the reduced viscosity versus concentration and get the intrinsic viscosity from the intercept. So the reduced viscosity versus concentration gets a straight line, and the intercept at 0 concentrations, the intrinsic viscosity. Let's see, no, the slope of that's the intrinsic viscosity. The intercept is the solvent, should be the solvent viscosity. Right, so you get, from the slope, you'll get the intrinsic. These are at different, what are these? These are different molecular weights. So the slope changes because the density changes with the size of the chain. Right, it's going to be, the intrinsic viscosity is going to be molecular weight to the A power. So as you change the molecular weight, the slope changes. So that's the idea of this. So I guess I asked that question so that you would get a feel like you could do the, you could build this thing. He shows what it looks like. It's a simple thing. It's basically you're getting, molecular scale information from something you could make, yourself. And then he gets this size distribution from the micrographs. Anyway, this is what he sees. So he goes across. This is the specific viscosity. So that's the that's your time minus time zero over time zero, right? That's the specific. That's where he's getting the specific viscosity from. And then the reduced is the specific over the concentration. You're going to plot the reduced versus concentration. And you got the slope of this is the intrinsic, which has units of milliliter per milligram. It's got units of inverse concentration. So the intrinsic viscosity is not a viscosity, right? What it is 1 over C star, 1 over the overlap concentration. It's the density, kind of the density of a single unit, a single chain, or in this case, a single sheet. So it's the density of a single sheet that's spun around. It's the hydrodynamic density. So it's the hydrodynamic volume and then the mass. It's the mass divided by the hydrodynamic volume. Hydrodynamic volume is the hydrodynamic radius. And it's like 4/3 pi hydrodynamic radius cubed. Right, so this is a sphere. And then that's a sphere. So the hydrodynamic radius is an equivalent sphere that gives the same volume that you're observing in this measurement. Right, so if your objects are spheres, the hydrodynamic radius is the sphere radius. If your object's a polymer, then all bets are off what this is. It depends on how much a solvent is drained from the object. So if you have an object where it's completely drained, the hydrodynamic radius could be the diameter of a polymer, or it could be the thickness of a graphene sheet. If the solvent hooks to it, so it carries all the solvent with it, then it can be the end-to-end distance. So there's a pretty big difference between the diameter of a chain and the end-to-end distance. They're going to be like 1 or 2 orders different in size, right? So the hydrodynamic radius can be a lot of different things depending on how the solvent interacts with the polymer or with the graphene sheet. Right, so it's a little bit of a mysterious object, but basically it's been tabulated at certain temperatures, solvents, and within molecular weight range into this Markov function where these numbers A and K are listed. So if you do a measurement and you can get the intrinsic viscosity with this homemade device, then you can get, as long as you do it at a fixed temperature and a known solvent, then you can get the molecular weight from that. The molecular weight you're going to get is called the viscosity molecular weight, MV. The viscosity average molecular weight. So if you remember, there's different molecular weights. So you have a distribution. You have number versus molecular weight. And so you're going to have, say it's polyethylene, it's going to have bimodal, could look like that. Right. So you could even have molecular weight averages from modes. The mean is going to be the first moment. Right. It's the sum of the molecular weights over the number is the mean molecular weight. Right. Normally you don't use the mean. Right. That's called a number average in for polymers. The second moment is the sum of m squared over n. and that's going to be squared. So that's the average m squared. And if you take, so that's going to have units of molecular weight squared, so that's not much of use. So you take m squared, the second moment, and divide it by the first moment, and that gives you mw, the weight average. The weight average molecular weight. And then there's also a z average, which is the third over the second, that's mz. Right, so you can get different molecular weights for polymers. The viscosity average is usually between mw and mz. So it's a high order moment, meaning it's a high value. The larger these values go up. So mn's lowest, mw, m viscosity, mz. They don't usually go higher than that. Because if you look at the distribution, so if you plot number versus molecular weight, to get mw, you're plotting number times m. So that's going to skew this curve, like make the high end look bigger. And then for the z average, you're going to do number times m squared, so that even skews it even more. And so it makes this small thing look a lot bigger the higher the order of the moment, and shifts the average to the right to a bigger number. Right, so that's kind of the idea of how this molecular weight thing works. And the viscosity average is some odd moment that shows up kind of in the middle. So it's not going to be the same number unless you're looking at something that's monodisperse. So for a monodisperse sample, then mn equals mw equals mv equals mz. For monodisperse, where you have number versus molecular weight as a spike. It's just a spike. Right, so when do you get monodisperse? You can make like monodisperse polymers. Right? You can synthesize it anionic polymerization. You can get something close to monodisperse. If you take mw over mn, then monodisperse, that ratio will be 1 because all the moments are the same. But if you have something like polyethylene, that number is like 12. If you have an anionic polymerization, it's like 1.05. This is called the polydispersity index. Right? So it's basically you can get a range of values. The best you can do synthetically is something like 1.05 to get that distribution. There's another way you can get 1. Okay, you can run your polymer solution that's got all different sizes in it through a gel. You can pump it through a gel at high pressure, called high pressure liquid chromatography or gel permeation chromatography. And then as it comes out as a function of time, you get different fractions. And those fractions are monodisperse. mw over mn equals 1 for each of the fractions in time that comes out. The high molecular weight ones find an easier path through the gel. They come out first. The low molecular ones can't find an easy path, so they find this convoluted path. They come out later. So you get basically this curve in number versus molecular weight coming out. And each of those, if the flow is slow enough, each of those is monodisperse, which means that any method to measure the molecular weight will give you the same molecular weight. Meaning you can run that through a viscometer. So at the end of that, you can run it through a viscometer. So one channel would be the solvent, and the other channel would be a solution. And then from the comparison of those two flow times, then you can just, since it's monodisperse, you can just get the molecular weight from that using the Markovnik equation. Right. So it's for, and then you'd have on the scale instead of time. So you'd have this curve instead of time. You can swap it with molecular weight. So you have retention time versus concentration. You change this to molecular weight using the Markovnik equation. If you had a viscometer attached to a GPC, that's the common thing that's going to be done in a lab. So Anyway, so he's got this curve. He measured it with this um, I can never pronounce that. The U viscometer, right? So, and then he plots the specific viscosity versus concentration, and he finds this transition, right? So normally, this is what's seen this is actually a polyelectrolyte, right? So, but there's going to be a difference between the C star, where you see if the first transition and then the entanglement, right? And this is quite a big difference in this case of the polyelectrolyte. So these are orders, right? So I think it's log base 10. So this is like 100 difference in concentration. You first see C star at a pretty dilute concentration, 10 to the minus 3 moles per liter. And then at some much higher concentration, you see the entanglement. Right in the, let's see, in the notes here. Here. So this is comparing a linear polymer. So the red one is a linear polymer. I mean, a red one is a not charged. It's the same polymer, but this is actually Colby who wrote that book, the polymer physics book, but this isn't in his book. Anyway, so he's going up in concentration. You see this orders of magnitude here in concentration, and then he sees a transition. That's the overlap transition for the chain that's not charged. And then the same chain, he adds charge to it, and he gets the blue curve. So where this shoots up is the entanglement concentration, and where that changes from 1 to 1.3 is this overlap concentration, 0.1 molar. Right? When he charges the chain, everything changes, but basically he still sees power 1 in the dilute condition, and then he sees this weaker dependence in the between the C star and the entangled chain part. Right, so the entangled chain part, it's got a steep dependence in concentration. This overlap part has just got a weak dependence. Right, so basically, this is the kind of behavior you're looking for. So in this paper, he sees this kind of increase in slope. It looks a lot like basically the uncharged linear chain, right, where there's a weak increase. So there's another increase where it actually has entanglement. There's a weak increase here. So this is acting something like an uncharged chain. Basically, there's some issue about the whole thing is that there's an issue between separating the overlap and the entanglement. They aren't the same number. They can be 2 orders of magnitude difference for polyelectrolyte. They have different signatures in the concentration dependence of the specific viscosity. So here he's got that C star shows up, and he just picks that number off and then plots it. Right, but basically there's another point. It's hard to see how sheets could become entangled, but nonetheless, these graphene oxide solutions form a gel. So they gel at some point, as do the clay sheets gel, and they make a kind of strange gel. So it's a gel. You can see it's a gel. Like if you turn it upside down, it holds its shape. It doesn't flow. So that's a gel. But if you put this under any kind of shear at all, it immediately becomes a liquid. So it's thixotropic. So it just flows immediately. If you stir it with a stir bar, it just turns into water. Right? But if you turn it upside down, so in a low shear situation, it's stuck, it's solid. Right? So it's kind of an odd gel that it makes. So the gel that it makes, I mean, somehow these sheets, if you figure out like what they have to do, so they've reached overlap, So they don't entangle in the sense like that kind of entanglement to make that would make a gel and a polymer. That's why he sees this steep concentration dependence. Right, once he gets to entanglement, is because he's got something like a network forming. Right? Here you form a network. I mean, they draw pictures of it like it's a stack of cards. Right, so you have this weird network of cards stacked, almost like the ends of the things are stuck together. Right, that's how they draw a picture of this gel. It's somehow a 3D. I've drawn almost 2D, but it's going to be a 3D space filling going across millimeters of this network of these nanos. So these are going to be 100 angstrom objects that fill up millimeters to make it into a gel. Right, so somehow it does it. The exact, because it's totally black, so you can't shoot a light beam through it, and it limits what you can do with this stuff as far as analyzing it. Right, so like IR spectroscopy you can't do because it's black. Right, it absorbs. So basically, viscosity is probably one of the only things you can do. So you have to kind of eke out the information you can get from this. Anyway, this C star exists, right? There is an overlap concentration. It looks a lot like the overlap for uncharged polymers, right? The overlap and the entanglement link up in that case, almost, right? They don't exactly link up, but so basically. So only a theoretician or a physicist would seek out this 1.3 power. Basically, there is a 1 power, which is just that the viscosity is proportional to the molecular weight. And there's a steep part where you know that's entangled. Then in between, there's kind of a decade where it almost has a 1.3 power that's predicted theoretically. So you say that that's overlap and this is entanglement. The behavior here is going to be kind of similar to that. I mean, he calls it overlap concentration. If he calls it overlap concentration, then you can plot it against molecular weight and get this power from this thing. Try to get the fractal dimension out of this, right? Which is kind of the point of the quiz. Like, what's the fractal dimension of this thing if you did this measurement, right? So you get C star versus L. You know, L is the square root of the molecular weight. So then if this is C star equals L to the 0.87, you have C star equals, for C star equals M to the 1 minus 3 by df. You know, df is 2, so expect this thing to be M to the minus 0.5. The way I did it. Yeah, that's right. So you know that M equals L squared. So if you want to put this into L's, that would be L to the minus 1. Right, because it's a sheet, you have L on each side, L squared is M, so you get L to the minus 1. So that would be that's his 1 slope here. It should be minus 1. He gets 0.87, which means that this df is 2.2, I think. So you have this is this times 2, so you have 2 minus 6 by df equals 0.87. So you get 2.87 divided by 6, 1 over is df, which I think is 2.2. Which means that you started with a sheet, df was 2. The only way to get, if you're not going to put branches in, is to crumple it up. So df equals 2.2, and his theoretical thing is 2.5. Let me see what that number actually is. 2.1. This is 2.1. Right. So that's one way that he goes at this. The other way is to take the intrinsic and find out what his Markoink coefficient is. Right. So So the Markoank is the same deal, right? You have viscosity equals mk times m to the a. And viscosity is going to be m over volume. So it's r cubed over m. And r equals m to the 1 by df. So you're going to get m to the 3 by df minus 1 for the intrinsic viscosity. So if df is 2, it's 0.5. If df is 2.5, then that number is it's going to be smaller than 0.5. Right? I mean, 2.5 is the theoretical one that he mentions. So it's 0.2. We did that already, 0.2. Right, and he gets 3.34. So 3 by df minus 1 is 0.334. And then 1.334 divided by 3 is df. So 2.25. So something like similar to the one we got before. I mean, the two numbers are different, but they're kind of close. So it's kind of an interesting paper. It's got to do with this intrinsic viscosity business that we've been looking at. There's a couple other papers that are interesting to deal with this graphene, right? So I thought these are actually referenced by him. So he's talking about this is in Nature. So this is the same Tanaka guy that did the penny PAM thing, the penny PAM gels. Polyisoproyl acrylamide, PINAM, whatever, gels, right? The thermal dependent gels that collapse when you reach kind of body temperature. Right? This Tanaka, we saw a paper by the same guy. And it's with a group of other people from he was MIT at the time, now he's at Tokyo. Then there's some other people from Japan and from Harvard, right? So, and this is in the 90s, 92, I think, 93, 92, right? And he's got, this is the same thing, it's graphene oxide. This White's guy is a famous guy working with this kind of sheet structure thing. Anyway, so he shows this is this intensity versus Q for these graphene oxides. I don't know how he got this data because it's black, but basically he got the data somehow. I guess at MIT you can afford anything, so he got some gigantic laser. There's no, it's in Nature papers, there's no experimental. They don't explain how they got it. Anyway, if you look at that, this is something kind of interesting. So you can take that data and digitize it, and you get things like this. And then you'll see, this is log intensity, log Q. What you see is that it shows the 2.5 that they want because it's there. This line here is 2.5, right? So it's pretty good at 2.5. These are different pH values. So I think the structure is changing with pH. But then if you look at the high end, this goes to 2. So this is pretty reminiscent of a polymer where you have a persistence length, right? So you have, this would be power 1 for a polymer because it's got a rod persistence. In this case, it's power 2 because you have a sheet persistence. So locally, at some extent, it's got these alkene bonds, right, that are planar, and they're conjugated. So somehow it's going to go off and planar. Everything's planar. So it's planar linked to planar. It's planar, right? So it's going to have, this will also be planar. So the whole structure is planar as long as it's got conjugation, right? So anyway, or if you can draw it that way, but Right, so that whole thing, every one of these is planar. So everything they link to, as long as it's conjugated double, single, double, it's going to be planar. So the entire thing has to be a sheet. You can't bend that until you stick in an oxide, a hydroxide group. And then all of a sudden that can bend. Right. So oops, I'm not showing this thing. So then it can bend once you put in the hydroxide group. Right. So it's going to be made up of primary or persistence units that are 2D, and then it's going to transition over to this kind of crumpled thing. So if you blow up, you'll see 2D, which is the definition of a manifold, right? So anyway, you can see the 2D here, and you can measure the size of those things. Like for this red one, it would be, this is in microns, so it's 2, it says angstrom, but it's really microns, it's 2.8. 2.8 inverse microns, right? So the size of that thing is 2.2 microns. And 2 pi, so if you take 2 pi over 2.2 microns to the minus 1, you get 2.2 micron. That's what I got anyway. Or 2.8 microns to the minus 1 is 2.2 micron. So you have the size of these sheets are 2.2 microns, and the other end, like where this tails over, is something like put that here somewhere. Where that tails over is 100 or 10, 12 microns, so 20 microns, this radius. So it's got this total size of the sheet is 20 microns, and these bends on it are 2.2 microns. So there are about 10 of these flat units across that are making it into this kind of self-avoiding walk. And then the total size of that thing's 20 microns. Right, so this kind of thing, I'm not sure how he got the scattering data because it's completely black, but basically you got it. And then it shows that same kind of behavior, the behavior similar to what a polymer would be, persistent polymer. Anyway, so why don't we call it quits there, and then I'll see you guys on Wednesday. So unless there's questions.